Hello, good morning and good evening. Welcome to Data Analytics Colloquium. My name is Carl Ho, and the co-host of the Colloquium with the other side, and Professor Peter Pan at the NCHU in Taiwan. And tonight we are really excited to have a couple of guests, very special guests to give a talk. And allow me to have Dr. Pan to start the colloquium. And Dr. Pan?
Yes, thank you, Carl. Good morning, good evening for those who are in US, and good morning to you who are in Taiwan. And thank you for coming and joining us today. And let me just briefly introduce DEC, this colloquium. Actually, we started this colloquium like 3 years ago, and the purpose here is to introduce the latest in data science focused on the application in broadly social, political, and policy sciences. And I think it's been a good run and until today. So we invited the top-notch scholars and the researchers in this field, and then try to bring to the audience those methodology or methods that we use, and definitely for all the guests that we invited, they have much to share. So today we have Dr. Granato and Dr. Wong today right here to introduce their research. And so I think this is a great honor for me to be sitting here to be a co-host, and I have to say a special thanks to Dr. Carl Ho for his dedicated invitation to all those well-known scholars. So I'll turn the microphone back to Carl and let him introduce today's guest speakers.
Hello, this is really my honor to introduce our very special speakers and guest speakers, and give me some. Please be patient because we have a long list of accolades that both are highly achieved scholars. And Dr. Granato is the Dean of the Hoppe School of Public Affairs and professor at the University of Houston. And he said he's a native of Chicago, and so I don't know whether you can tell from his accent, and you very soon you can tell. And Dr. Granato is the University of Houston Energy Fellow. Before he comes to the Hoppe School, he taught at the University of Texas and also the Department of Political Science at Michigan State University. And his teaching research interests include American politics, political economy, public policy, econometrics, and the unification of formal and empirical analysis, which is the theme of tonight's talk. And his professional experience also includes services at the Political Science Program Director and visitor scientist at NSF, National Science Foundation. So that is at the foundation, he helped develop and implement the EITM, and the full name is Empirical Inferential Theoretical Models. And then Dr. Granato is author or co-author of multiple books and publications, and he published in HAPS, Economics and Politics, a Journal of Theoretical Politics, Microeconomics, Dynamics, Political Analysis, Political Research Quarterly, and Public Choice, and Southern Economic Journal. And his research is very extensive, and but his book and the role of policymakers in business cycle, and another book, Empirical Implication. I'm sorry, it's not inferential. Empirical Implications of Theoretical Models in Political Science. Both are published by the Cambridge University Press. And now the other scholar, the other speaker that we featured tonight is Professor Sunny Wong. Professor Wong is Associate Dean for Graduate Studies and Professor in the Hoppe School of Public Affairs at the University of Houston. And before his various roles at the Hoppe School, and Dr. Wong taught in the Department of Economics at the University of San Francisco, and He was also an honorary instructor at the Essex Summer School in Social Science Data Analysis and Collection at the University of Essex in England. He has published research articles in academic journals such as AJPS, American Journal of Political Science, World Development, Macroeconomic Dynamics, Economics Letters, Computational Economics, Economic Inquiry, Electoral Studies, and Financial Research Letters. Dr. Wong has co-authored 2 books with Dr. Jim Granato, The Role of Policymakers in Business Cycle Fluctuations, and the theme of tonight's talk is also the same title, There are Empirical Implications of Theoretical Models in Political Science, and published by Cambridge University Press. Thank you for your patience. I know it's a long list, but without further ado, allow me to introduce the 2 scholars and the 2 special speakers, Dr. Jim Granato and Dr. Sunny Wong.
Thank you. Thank you, Carl. Thank you, Peter.
Thank you.
And welcome all of you
today,
tonight, whatever it is. I want to start by saying that what we're going to do is cover parts of our book. I'm going to summarize the first 3 or 4 chapters. And then the second part of the book, which is about 10 examples, Sunny's going to take one of the examples and go through the process of calculation and implementing EITM. So to start, the background, what led to EITM being created? It started in graduate school. I had a mentor named John Aldrich when I was at Duke. He encouraged me to take lots of courses in methodology. And he also encouraged me to take classes in disciplines that weren't in political science. So economics was a primary discipline I also took technical courses from. At the same time when I was at Duke, a very fortuitous thing happened. I met Marianne Stewart and Harold Clark. And I'll talk about their influence on me a little bit later, but they had a big impact on EITM. So in graduate school, I'm learning econometrics, all these things. And one thing that started to get me to think about EITM, remember, it was a baby step, but it was just being dissatisfied with things like dummy variables. Oh, and by the way, feel free to interrupt me anytime you want during the course of my discussion. I'll be glad to clarify anything. But I was taking these classes and they would use concepts like expectations or learning or things of that sort. And they would use a dummy variable for that very important behavior. And so I didn't know how to model there. But I thought, why do you use a dummy variable for things like that when it's just it's 1 or 0? It covers what the data separates into, but it really doesn't model those behavioral traits that we have. So that was the first kind of inkling that I thought, we had to do better than this. And then as I was taking the economics course, I noticed that they actually did model expectations. They did model learning. And I also noticed that the expectation modeling form it took had very important theoretical implications. That is, you assume expectations in one direction, it will lead to certain types of predictions. If you assume different type of expectations, it will lead you to a different set of conclusions or predictions. So that was also important. That gave me a thought, well, ex ante, when you start modeling something, that will drive the direction, but you also have an alternative model that can drive another direction. You have to figure a way to test those. But that was a very important lesson too. Now I moved from thinking about dummy variables to modeling, but also the modeling told me before I even got to a test, I could toy with the model and see what I got. And I could also manipulate it and use different assumptions, and it would also get a different result. So that was very important. Another thing in grad school that happened was I took some classes from econometrician David Hendry, and he introduced me to the London School of Economics approach to econometrics. And one of the things that they teach you there is you should never use weighting procedures or things like generalized least squares to correct your model. And the argument is this: whenever you specify a model, it's an empirical model. The residuals, if they behave randomly, that means the model does not have systematic error in it. But if you have something like serial correlation or heteroscedasticity, there's something systematically wrong in the specification, in the theory. So you should not, in his mind, his argument was, it's unscientific to go and do some type of Price-Weinstein correction, or was it Beck and Katz correction, things like that, because that doesn't take care of the problem. in the metaphor he would use is it's like you have a crack on a bridge and you're just painting over it by these statistical patches. It has nothing to do with your theory. So your theory's wrong if you have systematic error in the residuals. So that further pushed me in the direction of say, okay, we got to think of how to model these things. And another thing was, you notice a lot of times that you have to estimate systems. So that led to learning simultaneous equations, calculating reduced forms. When you calculate reduced form, the parameter isn't just one parameter. It's a set of parameters. So you have to figure out a way to identify those. Theory helps you with that as well. So that was another thing reinforced using theory in the modeling procedure before you even got to the test. So those things are in my mind when I started my first job at Michigan State. And over the course of time, I basically did research that was purely empirical. That was my training, particularly in time series. And then what happened was I started looking at, I was just making some time series regressions, and I noticed, I started thinking the rho, the Lagrangian variable parameter, the rho, the R1 coefficient, I started thinking, it moves around. We got all these tests for that, right? There's ways to estimate a parameter moving over time and watch how it fluctuates, recursive least squares, for example. But I started thinking, why can't we endogenize that? Why can't I create a theory that predicts the behavior of that parameter? Instead of just letting the data tell you what it is, let's create a theory, a model that shows where it should move. So now we're going to endogenize the parameter. It does a couple things. One, it brings in theory and ties to a test very closely. Another one, it takes care of the identification problem. And you're never even thinking about GLS. So you've broken through all of that, and you're targeting the parameters. And I did my first paper on that, dealing with reputation and credibility. And I started looking at how to estimate reputation with a theoretical model. And I created something using it. And it's in the Journal of Theoretical Politics. I published that in like mid-90s. But that was when I was on my way. And the final thing, when I was doing this, I reached out to Chris Aiken, who is an economist. He's one of the founding fathers of political methodology. Just a wonderful man and brilliant. And this is in the 90s. I said, Chris, I've been thinking about these parameters. I said, shouldn't we be trying to endogenize them? And he said, Jim, that's exactly what we should be doing. So he reinforced my bias to keep moving in this direction. I took a sabbatical in 1998, and that's where I met Sonny Wong. He was a graduate student in economics. I was trying to bone up my skills because I knew what I wanted to do, but my skill set wasn't there yet, particularly on the modeling side. I knew the empirical side pretty good, but the mathematical modeling part, the formal part, I had some skill in it, but I didn't have enough. And so I took a sabbatical, spent a year at the University of Oregon's economics department, plowed myself in a bunch of courses, and Sonny was someone that worked with me all the way through. And then we started a collaboration, which has lasted, 150 years now, right, Sonny?
More than that.
So
That's
I come
2
back,
centuries.
Yeah, exactly. I come back from the sabbatical and I get a phone call. This is where Marianne Stewart comes in. Marianne Stewart asked me if I wanted to work at the, interview for the job at the National Science Foundation. And I was like, no, because I don't want to be an administrator. Look what happened now. So she said, no, think about it. It's a really good job. He said, you could also do a couple things. One, you have to process the grants. The other thing is you can create, you can start a program there. You can do something entrepreneurial. Well, here's my chance. I now boned up my skills coming back from the sabbatical. I now was ready to start doing this, EITM. So I went, I got the job, and we instituted the EITM program there. Let me also say something about Marianne and Harold. We had a workshop on EITM, and I'm going to discuss it. You'll see in some of the presentation slides, you'll see some of that. What's important there too is there's a report that was done. I wrote it and I gave it to Marianne to edit. She fixed it 100%. I mean, that report is as much hers as it is mine. So it's online, still, it's 20 years old now, but it's still there. You can still download it and read what we decided to do with the EITM. Okay. There's 4 parts that I'm going to talk about. Let's start with the introduction and background. So the motivation, there's 3 things about EITM. It started at its National Science Foundation in 2001. There was a motivation followed by problem diagnosis and remedies. In terms of motivation, and this comes from the report, by the way, the EITM report I mentioned before. Political science was in a little bit of trouble at the time in NSF. They were cutting our budget or not giving us very big increases in money because our bosses at the time thought we weren't doing very interesting work. They thought the empirical work wasn't very good, and you weren't tying theory to test. So there was a negative perception of political science in NSF, and we thought EITM would be a way to help reinvigorate our reputation. So that's what happened. In addition, during the workshop, our boss, we were going through this, and he was skeptical. He thought maybe the community wouldn't respond, that there wouldn't be anybody who would want to do this. So he thought this was too far ahead of what the discipline was. We disagreed, and we think in the end we were right. It's not, EITM is not dominant by any means, but it's something in which we think is something that political science, political economy will be moving in a broader direction for the next 20 to 30 years. We just think it's just going to take a longer time because the skill sets are not necessarily as strong as they should be. And I should add that when the ANES was started in the 1960s, very few universities in the United States and outside the United States was doing survey research. And so when people like Warren Miller go to Scandinavia to go and talk to faculty, they wouldn't show up. Only the students would show up. And 30 years later, they all had their own ANES. They all had their own survey operations. So you have to play the long game here about something like this, especially when you're challenging a profession in such a direct way. Okay, so the first thing was there was a weakness in the discipline. The second motivation was there were old antagonisms. At the workshop, we had both empirical modelers and formal modelers there. And we had a couple people that could do both, like Richard McKelvey. And you had people that are transitioning to doing, like Chris Aiken. But for the most part, you had one camp or the other. And the issue, we had no idea whether or not they'd get along. We thought they may start fighting. Who knows? I mean, would they think the EITM idea was stupid? Blah, 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 blah. Well, as you can see from the quote here, and it's also in the book, they got along. And also, they agreed it was a problem, that we needed to figure ways to merge formal analysis with empirical analysis, or formal modeling with empirical modeling. The third motivation was the research design NSF competitions. This goes back, and it's attached kind of to the first motivation, that, you know, our boss was saying, look, I've had almost 20,000 proposals. A lot of times the theory and test aren't even linked. They're linked in a vague way. They say, I've got this theory and I got some data, but it was difficult to see the tie-in. So it was just straight empiricism without much theory in his mind. So that led to a lot of rejections. And he thought, and he did agree, even though he was skeptical of whether or not it would be implemented in our profession, he did agree that this was an important step if we could implement it. Okay, the problem diagnosis. There's about three or four areas, a couple areas here that are important. Next slide, please. So the first thing is we looked and we discussed this. We would call it compartmentalization. That is, and if you're in a particular subfield, there's typically a certain type of method you use. So when we were going to grad school a million years ago, if you were in comparative politics, you did case studies, you did qualitative analysis. There wasn't a lot of data yet. So the comparative politics folks were primarily qualitative people, so they didn't have any time for formal empirical work, statistical work, let alone formal work. So that's one reason. So with the Americanists, the people who had data and voting and things like that, they had all the statistical procedures. And some of them did formal modeling too, and some actually merged with very few. But there was a whole difference between what type of field you were in and what type of methodology you were using, as opposed to learning all the methods you can and applying it to your particular field. So the field dictated your methods, and that harmed the profession. The training was siloed, another bad issue. So if you're training empirical analysis, you're just learning empirics. You're learning time series, you're learning cross-sectional analysis, you're learning maximum likelihood, you're learning cross-section, pool time series cross-section, all of those things. Your Lizrow, Logit, all of it. You learn that, but you'll learn how to model. On the other hand, if you're at Rochester, there's a few places in political science that emphasize modeling. Caltech would be another, but a few, not a lot. They were strictly about theory. So you put your mathematical models together, you did the derivations, you got your result, and that was the truth. You didn't test anything. So you had the compartmentalization problem, and then you had silo training. That is, you took one track or you took the other. And most people in political science took the empirical route because the math was too damn hard for formal modeling. But the result of that is this. The empirical modelers saw any type of statistical problem requiring a statistical solution. The formal modelers didn't give a damn about testing. And those were the two tracks we were headed on. Now, factors that reinforced this was the intellectual investment. Empirical modeling is less difficult mathematically. That's a fact. So the intellectual investment in that is, if you're not as strong in mathematics, you drifted towards empirical modeling. On the other hand, if you're really good in mathematics, you became a formal modeler. You became exotic, because there weren't a lot of them. So you had people like Jeff Banks or David Austin Smith or, well, Dick McKelvey. But Dick McKelvey could do anything. I mean, he was doing EITM before anybody. I mean, he was amazing. And of course, there's also training differences, right? You focus on measurement, data collection. If you're an empirical modeler, if you're a formal modeler, you focused on mathematical rigor. And the research practices, I've already talked about, I'll briefly summarize them again. Research practices were statistical problems in your statistical model required statistical solutions, which led to GLS and all kinds of other non-falsifiable procedures. They had nothing to do with your theory. On the other hand, for formal modelers, you had theories of unreality. A lot of times you just did something that was fancy, but what the hell did it really mean in the end? So you was divorced from any type of empirical or testing feedback to update your formal model. So the remedies that we decided on in NSF in 2001 were, we're going to have training and retraining for students and for faculty. And we also had conferences and workshops. And finally, we want to establish some research work groups. Of those three things, the one that's lasted the longest are the summer institutes, the education, the research the training and retraining. We've had, and if you turn to the next slide, you'll see how many places have had those in the past 20 years. And we'll have another one at University of Houston this summer. So COVID and other things led us to shut it down, but we're going to start again. It could be we'll do a combination of face-to-face and virtual. But that's what's lasted the workshops. Some places do it for 2 weeks. Some places do it for 3. At Houston, we do it for 2. And we have a very specific reason for doing that. But it's, when I was director at NSF, I went to the other ones early on. I saw what they did, and I thought, I think I would do it this way. So the way we're doing it is a revision of what I saw other people doing in the past. We do it for 2 full weeks. Oh, by the way, Sunny is one of the teachers. Okay, let's get to the framework. Okay, so EITM, what is it? It's a method or a mindset for merging formal empirical analysis. I think you got to go back a few slides. It'll be number 2. There you go. No, keep going.
Okay.
There it is. So all it is, you're merging formal and empirical analysis. You treat them as unified. Okay. The second thing about it is there's more than one way to link formal empirical analysis. We have 9 or 10 examples in the book, and you'll see this. It's driven by your behavioral, your formal, behavioral/formal, and your empirical concepts. That drives everything. You search for tools to test those, model and test those. Okay. So what's the framework look like? There's 3 steps. The first is you identify and relate focal concepts. That's the behavior part. So what do people do? And the list I have here is not exclusive. So there's more than this, but here are some of the things we know that people do. And depending on your theory, some of these things may be important to what you're doing. So people make decisions, they bargain, they have expectations, they learn, and they also interact socially, sometimes strategic, sometimes non-strategic. In the example that Sonny's going to give you, there'll be social interaction, but it's not strategic, so no game theory. This is going to be straight modeling where there's going to be one group takes information from another. Now, empirical concepts are things like persistence, measurement error, nominal choice, simultaneity, and prediction. If anybody has any questions about those, please interrupt me. No questions? Okay, so here's the trick. How do you bring those two different types of concepts together? Analogues help you with that. So in step 2, so you've got a story, right? In step 1, you've got your story. You've got some theory about something, and you see these behavioral concepts, you see these empirical concepts, they're in there. And you got to figure a way to model them, but most importantly, you got to tie them together. So this next step, and the most important step, well, probably not the most, it's a very next step, a very important step is you have to use analogues. And an analog is not just something we call operationalization. It's bigger than that. It's a broader concept. And an analog is a tool or a device that we use to create a concept or to measure a concept. So when we talk about decision theory, what's the way to model that? Well, you use decision theoretic modeling, use utility maximization. You just create the utility function. For expectations, you can use conditional expectations procedures. For learning, you can use adaptive learning or Bayesian learning. Again, these are not the only ones, but these are some. And for strategic interaction and social interaction, you can use game theory. So those are not, now you've taken the behavioral concepts, here are the way to take these and model those. Now for persistence, we use autoregressive, that's a typo right there. It should be, for persistence, we use autoregressive estimation. For measurement error, we use error and variables regression or instrumental variables procedures. For nominal choice, we use discrete choice modeling as logit, probit, things of that sort, or multinomial logit, multinomial probit. For multi-stage estimation, for simultaneity, that empirical concept, you use multi-stage estimation. So it's going to be 2-stage least squares, 3-stage least squares, things of that sort. And for prediction, you're going to use point estimates, just a number, in fact, or you can use distributions. You don't have to have a statistic. You don't have to have a statistical test with a p-value. Sometimes it could be just a straight number as a test. Now the third step is a step that in a revision of this book in the future, we're going to delve into to greater extent. But right now, you now take the analogs for behavior and the analogs for empirics, and you figure a way to merge them. And it turns out they're pretty sophisticated but transparent ways to do it. And that's what we found out in the book. We looked at numerous examples and said, hey, there's several ways we can do this, and you can put them together. And I should say in the book, if you don't know the tools that we talk about in the chapter, every chapter has an appendix that goes through the basics and the tools. So in this example, I'm going to talk about error and variables regression. We go through the entire process of modeling error and variables regression. That's the empirical part, the empirical analog. So it's right there, and I'll refer to it in the notes too. Same thing with using expectations and uncertainty, which will be part of the example. We have a way to do that formally. And what's going to happen in the end, I'm just going to give you the punchline. You're going to have the result of the empirical model and the result of the formal model look almost identical. So the parameters from the formal model are captured in the empirical model in a transparent way. So there's not this loosey-goosey, the parameters moving around. Why? You actually can predict it using your formal model. And now you've got a test of that. So the third step is unify the analogs. Okay, the benefits. it helps with creating a cumulative science. And what I mean by that is, and you'll see the examples in the book, I think chapter 2 or 3, we talk about how Solo's model built a whole regime of other papers to follow that built on that framework. Or you see, I use Lynn Ostrom's work to show how what she did in experiments, how it's had a foundation, you can build on it. And I'll tell you why that's an issue in a second, but accumulation is very important. And if you have a formal framework that people can build on and add a variable or two, you can watch ex ante how the whole system changes. On the other hand, if you were to do this with an empirical model, you just add another variable or two, what you see is all the parameters flip all over the place. Very unstable. Edward Lemur has a procedure called EBA, extreme bounds analysis. I don't know if you've ever used that, but it's a robustness check on your model. If you stick in a variable, what you're looking for is to see whether or not the other parameters behave and they start moving in a very unstable way. That tells you, A, the model's probably not right, but B, it also tells you formally, if I knew how to set up this model initially with the math, the formal part built in, I could actually see what happened to the parameters if I moved something around or added something. So that's why you have that very important aspect of formalizing these things at the beginning. So, and that leads to compare contradictory ideas. That is, initially you can actually stick in a different specification and compare it to what you've got. Add a few variables here, whatever you want to do. You can watch how things fluctuate before you even test it. But once you've got that in place, now you can test it, and now you can really compare the ideas. And finally, test versus consistency evaluation. Again, once you formalize something, you can actually look if it's consistent with your formal model. That's very important. Again, the transparency is crucial here. So what we're saying here is you can accumulate a whole spate of research, a whole research trajectory. It may not be right in the end. On the other hand, there's a coherence, there's ties to theory and test as you go through, but maybe someone comes up with a whole alternative theory about the dependent variable in mind that blows it out of the water, that's got better forecasting properties and everything. But in the meantime, we're moving in a direction where there's something coherent and non-falsifiable. Okay, next slide. I'm going to go get to the example and just move quickly. EITM informs debates. I'll just focus on the last point. You're going to be faced with situations where theory is ahead of your data. There's a formal model is really spectacular, but the data stinks. You can use things like simulation or try and get a grant or something, get the data to test it. But you're also going to be faced with situations where data is ahead of theory. That we've got all this data is moving around, but we don't know really how to explain it well. EITM helps with all of that. Okay, let's go to the example. Now, Sonny's going to go through steps of a different example. He's going to go through the math. I'm going to just go through the framework and tell you how to think about these things, how we think about it. So this is the application in chapter 4. So this is about economic voting. Traditional economic voting was at the polls, right? Kind of like what's going on in the United States right now. On the other hand, that led to some people thinking maybe we can manipulate disposable income, make it go up right before the election, get voted in, and then the higher inflation, things like that would take over, and that would actually lead to a recession later on. So people like Alcine and Rosenthal came up with the idea, wait a second, what if people have expectations about all of this? And they actually can see that the incumbent administration's trying to manipulate them. And they forecast that there's an inflation coming, so why should I reward them with a re-election when it's actually going to hurt me long run? So they had a model, an idea where they will reward, so instead of rewarding for this boom bust, they'll reward them if they're competent. That is, their economic management over time, that is, the growth is stable, inflation is stable, unemployment, they'll reward them for competence. On the other hand, sometimes it's good luck. So there's uncertainty about evaluating administrations, income administrations sometimes. So is it competence or is it good luck? I have expectations, but I'm still uncertain. How am I sure that it's competence? How am I sure it's good luck? And that's your problem. You have expectations about the future, about the economic situation. Will this good behavior continue? or was it just good luck? And what do I do in terms of rewarding somebody about that? So, so that's the idea. It's also called the signal extraction problem, and they've been around in economics for many years. And there's two people that have used this type of work. Both have Nobel Prizes, Milton Friedman and Robert Lucas. So the uncertainty in the Alstein-Rosenthal model is competency and good luck. With Friedman and Lucas, for Friedman it was permanent versus temporary, the uncertainty about that. And for Lucas, it was general effect or relative effect. And they all use the same, so that kind of uncertainty with the expectations attached drove their predictions in their theory. So in EITM language, what is this? Well, step one means we're going to have to relate expectations, uncertainty. Those are the two behavioral concepts. The third one is measurement error, because for the test, we know that there's an error there's possibly a correlation between the error and the variable in the regression. So you've got a measurement error problem. So what we're going to do is we're going to take those two behavioral concepts and that one empirical concept. We're going to put them together. That's the first step. So we're not even thinking about the theory anymore. We're thinking just about these concepts, right? We'll bring the theory back in later. The second part is where the analog is going to be. Well, the analogs for expectations and measurement error, expectation and uncertainty are going to be conditional expectations and linear and recursive projections. That's what we're going to use for the formal part. And that's described in pages 71 to 74 in the appendix. For the empirical analogs, it's measurement error and error and variables regression. Okay, because we have to estimate this formal model at some point, and error and variables regression is the way you want to do this. That's described in pages 67 and 68 of the book. Next slide, please. So this is a synopsis of all the formalizations for all the description of the empirical analogs. This is just a summary of it. The thing I want you to realize after you go through the math, see that ratio right there? It says beta 1 with the ratio of sigma, what is that? Sigma squared x, sigma squared over sigma squared x with sigma squared e. That's your uncertainty coefficient. After you do with the formulation, where you take the expectations and linear projections, you get that ratio. And the behavioral implication there for the model is, if the sigma squared e in the denominator gets big, that drives everything to zero, meaning there's no positive effect of the competency. That is, the uncertainty and good luck drives it. So there's no benefit to the administration if people think it's all good luck. Okay, so keep that ratio in mind. That's the formal part. After we use all this behavioral mumbo jumbo, the formalizations, this is the empirical result. The empirical model. This is if we go through the math, that ratio is the result. This is an error and variables regression term is what it is. Now let's turn to the next slide. We do the same thing using conditional expectations and linear projections. This is, again, a snapshot of all the derivations you go through. We go step by step in the appendix. You can actually see it. One of the things that drives us crazy in looking at a lot of other work, we say it in the book, we say, we get to certain steps and there's like a bunch of gaps. So you have to guess what the hell the math was. In the appendix, all the appendices, we try very hard to give you every step. So if you've never seen it before, you've got it right in front of you now. But this is a summary. Notice the bottom. See that ratio? Once again, this time you have sigma squared mu over sigma squared u plus sigma squared epsilon. That epsilon is your good luck variance. Same behavioral implication as the previous empirical model I just showed you. And so there it is. You now estimate a model. You know the parameter in front of the change in the variable of interest. In this case, is the difference of GDP from its trend. That's less important. I just want you to think about how EITM works here. That parameter gets suppressed ex ante, but also if you test it, you can also look at how volatile inflation was, for example, and see what happened. And then you test it, and you can see if the parameter fluctuates or not. And you can also correlate that with behavior inflation during that period of time. And that's what the test involved by Ellison and Rosenthal. But that's how you do EITM. That's a simple example. You just tie in these analogs. And again, remember, you're focused on the parameters. Next slide, please. So,
allow me to interject.
Yeah.
Hi. I think this is so far. This is extremely interesting. Can you elaborate a little bit about the concept of analogues? So, are you only focused on the continuous variables, or this is something that could be empirically presented in a continuous variable? This is what you call the analog versus digital, or versus dichotomous. What is the analog in this case?
For which one? For this example?
The general example of analog. I think that you used analog. I think this is a really important representation of the concepts. And so you gave a couple of examples about analogs being maybe government competence. And can you elaborate a little bit more about the concept of analogs and how it turned into analogs?
Okay, so the concept first, the idea is that they're using, the behavioral ideas that they're using in their paper, Ellison and Rosenthal, are expectations uncertainty, right? So we have to figure out, so you have to create devices to model that. So we chose to use conditional expectations modeling and linear projections, okay? And that's how you get this result right here in this slide. So the analogs, the device, the concepts are the idea, the theory. So they talk about competence, good luck, and this is what the result will be. But you got to figure out the model and test it. This part right here, this slide right here, is the modeling part. The test, the analog part. We came up with some devices, and now this is the result of the device. And now that's the formal part. The other part is the test is you're going to do a regression of this, and it involves measurement error, right? The error you've got systematic error, and you have random error, and you have to figure a way to isolate that or model it. And if you go through least squares regression and induce measurement error in the mod least squares regression, you'll get that. Go to the previous slide. You'll get that same ratio. And so the idea is I'm taking the formal model, and then I have and the analogs for the behavior part, expectation uncertainty, and I have that's over here. And then I've got the empirical model, and I've got measurement error involved. And I'm going to merge them. And when I go through the math for both, I can prove that the parameters are linked. So when instead of just estimating an error in variables regression and doing instrumental variables of test of GDP beyond trend, how that affects incumbent, in vote popularity or something like that, what we're doing is we're saying, you're not just doing that, you're estimating it, but there's a formal model that has that same ratio, and you can actually determine where you think the parameters are going to go. You can actually have hypotheses that are very specific about the parameter. And that was my early on, is about you're endogenizing the parameter to theory.
Yeah. All right, I think we can move on. I have some more questions, follow-up questions, but we can do that later. Yeah.
Okay.
And sorry to interrupt.
Yeah, that's okay. And so if you unify all this on pages 76 and 77 in chapter 4, you will see the Ellison and Rosenthal result, which is exactly the same as the two results you saw before we had those ratios. Now in their book, in their chapter, they just go through and they give you the result. We went through and showed you how the empirical part, the error in variables regression formalization, and the behavioral formalization and expectation uncertainty were related. And I think I might have gone too long, so I apologize.
No, that's perfect.
No. I think you're just fine.
So shall I move on
You want
to the next
Yeah,
topic?
I think Sonny's going to give an example. It goes much more a deeper dive.
Sure. Yeah, I can do that. Thanks, Jim. First of all, I would like to good evening and good morning to everybody, and thank you, Dr. Ho and Dr. Pan, to inviting us to be here and give a presentation. I'm so excited to be here, and I would like to move on with like what Jim mentioned about like a general structure about what EITM is about. Now we want to focus on one specific example about how we do EITM in practice. And we've been talking, because in the book, as Jim mentioned, there are many different examples we've been doing like in the book. And because the thing is, I thought that when I was actually invited to give a talk here, we thought that inflation is one of the huge important issues right now globally. So that was the reason why we decided why don't we just talk about inflation expectation projects like this time for this presentation specifically. So you can actually see that the topic that we want to talk about today will be more about the information diffusion and also inflation expectation. And that will be the topic that we want to specifically focus on, the example that we specifically focus on today. Next slide, please.
Okay. I may need to share again. Allow me to do it.
Okay.
Break it and do it one more time.
Right. So, but the thing is, I can just briefly talk about it. The whole idea. When we are talking about this project, this specific example, actually is coming from a couple of papers that we've been doing, and as Jim actually mentioned, we met like when I was in graduate school, and one interesting thing is that like during that time when I was in graduate school, Jim showed me one of his paper. It's the Granato and Krauss paper in 2000. And that paper, he basically showed me a very interesting idea about like how inflation expectation can be transmitted from one group to the other. And what they found is that the inflation expectations from the highly educated group can actually affect the inflation expectations for the low educated group. And that basically what the major finding in that paper empirically. So that we will consider as empirical implication of that idea. And after that, because of that paper, and Jim and I would start working on how can we put it in a formal way. So we create a theoretical model to explain how do we actually see like one group's expectation can affect the other group expectation. And we create a theoretical model. And that's why we have another paper, the Granato, and Wong, 2008, and building up a theoretical model explaining about the information diffusion process. Like we use a very general macroeconomic model called the cobweb model to explain how that works. And that is what we consider as the theoretical models. And finally, we have the EI, which is the empirical implication coming from the Granato and Krauss paper. And we also do the TM, which is coming from the other paper, and that Jim and I and my another co-author, Aaron Guzzi, and do it together. And finally, we put these two papers together and create what we consider EITM paper. That would be the Granato, Low, and Wong. And it's nothing more than just like having one empirical paper, one theoretical paper together and make it to be EITM project. And I hope that will be a good example showing about how we do EITM in a separate way, but also in the aggregated way. And that's what we are trying to do. Next slide, please. So speaking about the EITM process, so we have, as Jim mentioned, about step 1, step 2, and step 3, right? So maybe I can actually help also provide more details about how we understand the behavioral concepts and the analog. And I hope that this example can also provide some more information about this idea. So when we talk about step 1, it's more about like how we understand the general behavior in the society. Like in the society, we have social interaction, we communication, generally speaking, like you and I right now, all of us right now, we are talking. This is the communication. It's a general behavior. And we learn. When we collect information from outside, when using information, we process After we process, we do our analysis, and after we have analysis, then we start doing our prediction about what we think should be doing. And once we do this, what happened next? And in this case, that would be what we consider as like a general behavior, how would that related to some kind of empirical idea. So in this case, we put social interaction, the information diffusion as our behavioral concept in this case. So in our case, the behavioral concept would be how we see, let's say, make it simple, the behavioral concept coming from two groups. We have the less informed group and a high informed group, and how these two groups are interact with each other. And through forming expectations as another behavioral concept and learning behavior, they learn by processing the information that they obtained from each other. And from there, we will be able to process the equilibrium from the model. And in this case, we find something is what we call the boomerang effect. That's the result we get in this model that I'm going to explain in more detail later. Next slide, please. So we need an analog. We need a way to actually put these together from these behavioral concepts into the specific mathematical formula. And in this case, the analog would be what we consider as rational expectation or adaptive expectation. That would be the formal empirical, the formal way in mathematical way, putting something that we see in the daily life into mathematical formation. And that's what we are trying to do here. We introduced a very, and now in this case, we try to explain how this model works mathematically. So we use a very simple model, just a macroeconomic model, nothing more than just supply and demand. But the supply and demand is with the expectations involved. So in this case, we use a very famous aggregate supply curve coming from Robert Lucas, what Jim also mentioned in his presentation. So basically, you can see the first equation here. YT depends on Y bar plus theta PT minus ET minus 1 PT plus error term T here. So basically, in this case, YT represents output. Output actually is related to expectation difference. Sorry, let me say it this way. The difference in the price level between the current price and expected price as the factors affecting the output level in the society. If price goes up, output goes up, supply, okay? And for this supply curve here, that actually would be related to the demand curve. The demand in this case would be what we call aggregate demand curve, coming from a very classical idea, aggregate demand, what we call a quantity theory of money, so QTM. So money supply and velocity, V, equals price times plus quantity. So in this case, from here, money supply will be the factor, which is like the monetary policy, can affect the relationship between price and output. From here, you can actually see that if money supply and velocity V, these two kept constant, then we can see that P and Y is on the other side, on the right-hand side. If price goes up, keeping the whole equation constant, Y must go down. So in this case, we can see the negative relationship between P and Y. That would be the demand idea. When price goes up, quantity goes down. When price goes down, quantity goes up. That's how we actually see the demand curve. So with the policy rules here, so we also include the monetary policy, which is money supply, depends on the past price level, and also some other information factor, which is WT minus 1. Some other factors can affect the money supply, which is the monetary policy, that affects the society, which is about aggregate demand curve here. And that's how we form the model here. And we can move on to the next slide. So for the next slide here, after we have the supply curve and demand curve, we can solve for equilibrium. And the equilibrium can be solved in this reduced form. That's what we call the reduced form of inflation dynamics. So we can actually convert the price level into inflation. Inflation is nothing more than a change in price level, right? It's just like PT minus 1 would be just the change in price. That would be considered as inflation in this case. So after solving the reduced form here, this can be considered as how we see having demand and supply interact with each other. We can see how inflation will be affected by the expected inflation, which is ET minus 1 pi t, plus other information, which is WT minus 1. And also we have all the parameters coming from the demand curve and supply curve. And then we can move on to the next slide. So now in this case, with the demand and supply, the reduced form here, we can solve for the equilibrium. And that is like, generally speaking, we can call that as a rational expectation equilibrium, REE. So in this case, assuming that all people are rational, assuming that all people actually knows everything, that's why we call rational expectations. We know people know everything. Then finally, we know that the inflation pi will actually depends on WT minus 1 with the parameter, which is A bar REE and B bar REE, and would be just like alpha over 1 minus beta and gamma over minus beta. With all the mathematics we calculate, we will be able to solve the equilibrium like this. So I can go over more, but the thing is, I think I want to go quickly to get to the what I really want to show you at the end. So I'll rather just show you what the result look like, and then we can move on. So in this case, we can see that when people making expectations about pi t minus 1, what if they are rational with all the informations, how they're going to actually form the expectation would be coming from the parameter A bar REE plus B bar REE times WT minus 1. This is the way for example, you and I and everybody with all the information available, which is WT minus 1, this is the way to form expectations to predict inflation at time t. Next slide, please. So now finally, so we have the general idea here, and now we want to do is that we observe what happened in the real world, that people interact with each other. And people actually have different information set, just like what Granato and Krauss actually show the results empirically. So the question is, how can we form a theoretical model coming from something that we observe in the real world? And that's basically what we are trying to do here. So we make it very simple, the model very simple. Here we assume two groups of agents, two groups of people here. One group actually what we call a more informed group, one group actually a less informed group. How do we define them? The more informed group means have more information set. In this case, information set will be WT minus 1. But now we break it down into two types of information from the WT minus 1. We have XT minus 1 and ZT minus 1. You can think about XT minus 1 would be the common information that is available for both the more informed group and the less informed group. The only difference would be the ZT minus 1. ZT minus 1 is only available for the high informed group, but not for low informed group. And because of that, for the low informed group, the only way they can get better predictions, a better forecast, is to interact with the high informed group so they can get better predictions because they communicate with others, create some kind of social interactions in the society. Next slide, please. So from here, we can actually now make the very simple expectations for two groups. For high informed group, they're going to use entire information, which is WT minus 1. That will be coming from XT minus 1 and ZT minus 1 to predict pi t inflation. On the other hand, for low group, they were only using XT minus 1, the common information. They don't have ZT, unfortunately, they only have XT minus 1. However, the one important thing here is that the low group would be willing to communicate with the high group to ask about what they know about the inflation for that period. So in this case, for example, let's say I'm the low group, I've actually asked someone like, what do you think about inflation next time? So someone actually, the high group will actually tell me, oh, you know what, actually it's going 2%, or it's, you know what, it's going to be like 8.5%, or whatever the information is. Oh, then I got the information. I use that information be part of my equation and to predict my own, to do my own predictions for next period. And that is the reason why you can see that on the second equations there, you have pi t minus 1 hat. So pi hat t minus 1. That would be the information coming from the high group that for the low group to form the expectation. And in this case, the pi hat t minus 1 we're coming from the expectation coming from the high group. That's why it's like E h t minus 1 pi t would be expectation from the high group with some kind of measurement error. Because the thing is, for the low group, when they get the information from the high group, they may not get them like in the perfect way. They may actually get it with some kind of noise. And the noise in this case will be ET minus 1. So now in this case, we create two groups of agents coming from an analog. Here would be the expectations forming in this way. Now the question is how people learn. You can see that in the very bottom here to see the process here. The high group form expectation using WT minus 1, which is XT minus 1 and ZT minus 1, and provide information to the low group. And so the low group will use the XT minus 1, their own information, and information coming from the high group to form their own expectation. And that is how we actually see the information diffusion, social interactions coming in to this model. We can move on to the next slide, please. Okay, so now in this case, after this, that we can do all the mathematical magic to create the equilibrium, and turn out we can find that people solving equilibrium, how would the high group form the expectations, and how would the low group form expectation? We're coming from the parameter AH, B1H, B2H, and also AL, BL, and CL. And these will be the parameters that the high group and low group would do to form the expectations pi t at time t. So in this case, for the parameters for high group, A bar H, B bar H, B bar 1H, and B bar 2H that represents the supply and demand from the model with alpha over 1 minus beta, gamma 1 over 1 theta, and gamma 2 over 1 minus beta plus beta mu times 1 minus CL. And that would be the parameters for high group. And then we also have the parameters for the low groups. And that would be the way how they form the expectations. One thing that you can actually see here from this model here, you'll be specifically about CL. And for CL here, you can actually see that the measurement error E, we see that E is actually the measurement error, like coming from the information coming from the high group to the low group, right? And the thing is the low group would not be able to interpret the information in the perfect way. That's why we have a sigma E squared for CL. And that means CL may not be perfect. It's actually between 0 and 1, mathematically speaking. So they would not completely getting all the information from the high group to make the formation forecast for the inflation. More importantly, another way to think that is can see the B2H. For B2H for the high group, now that becomes a very interesting situation because for high group, now after the interactions, their information ZT minus 1 for predicting pi t now is actually affected by the behavior of the low group, because the thing is, you can see that in the denominator, CL is part of the equation. CL is part of the equation. That means whatever the low group is doing can actually affect the high group's expectation. So that creates what we call the boomerang effect. Because the thing is, during the interaction, the information interactions going on here, when the high group try to be generous, giving the information to the low group, turn out we actually get a feedback and coming back to the high group, and high group get affected due to the interaction in the economy here. And we can move on to the next step here. From here, we can actually, not only we can calculate equilibrium in the model, we can also predict about the forecast error for two groups. That's what we call MSE, the mean square error. For the mean square error that we actually see here, that we can see the mean square error for the high group and the mean square error for the low group. More importantly, for the mean square error for the high group here, under the perfect situation, if all people are rational, for the high group, the mean square error, the error of the prediction error should be only sigma squared eta, which is the right hand side, that one, the sigma error. However, because due to interactions here, the high group actually receive a higher predicted error. So we have a beta mu C bar L square sigma square E, and that's an extra term for the forecast error for the high group. So in this case, that's C, the boomerang effect, that high group actually get worse off due to this forecast, due to this social interactions in the model. So what we are trying to do now in this case, we have the model prediction. The model tells us that due to the information diffusions, high group actually got worse off due to this model information diffusion. The question is, can we test it? Can we test it in the empirical setup? And that will be a next topic coming from the theoretical model. So that's why we can move on to the next slide here. What we want to show in this case is, like, according to the theoretical model, we can see that the high group, the mean square error, which is the forecast error, would go up. The error will increase if the predicted error, which is the sigma E square, increases. So whenever we have a more noise going on between two groups interact with each other, if the more noise between the interaction between two groups, the high group got worse off. So that is the situation that we expect to see. The question is, do we see this relationship empirically? That would be the EI part, the empirical implication coming from this theoretical model. We can move on to the next slide. So finally, we can unify the theoretical part and now with the empirical part. So what we try to do is we want to see question number one, do we see interactions going on in the real world? We know it does, but I think we want to confirm that. The second part is, once we believe that they interact with each other, the question is, do we see what we expected from the theory? That whenever we have a more interaction going on, when the interaction actually have more noise, with actually making the high group to have a lower predictive accuracy. Do we actually see that? That's why we are testing two things. First step, we want to test whether there's any kind of information diffusion going on. Second thing is, do we see the boomerang effect exist in the real world? And that's what we are trying to test. So we are moving on to first test, to test whether they actually have any kind of relationship. So to do that, we follow the Granato and Krauss idea. We use the inflation expectation data coming from the University of Michigan, the consumer survey. And one of the questions we use would be, during the next 12 months, do you think the price would generally go up and down or stay the same where they are? And that basically the question. And then by what percent do you expect the price will go up or down on average during the next period to actually measure about the inflation rate? And because I think this is a survey, so we can actually also further to break it down into different groups. We actually, based on the education, we can actually break it down to high informed group, which is a highly educated, and then low informed group, which is a relatively low educated group. And that's basically what we're going to do next. I tried to be a little bit quicker here, but this part will be pretty quickly. I can go through. Next slide, please. Okay, so what we are trying to do, we break it into two groups. We call group H and group L. Group H would be the group of the agents or the respondents receiving a college degree or a graduate degree. And group L would be those actually without a college degree. We even further break it down for the group L into two groups. We have the group L1 and group L2. For L1 will be relatively higher information, which is they are having some college or high school diploma. For L2 would be they don't even have a high school diploma. To break it further, to break it down to, like, basically we break it two groups, and for the second group we also break into the other two groups in this case. And on the right hand side you see the figures showing about the data, how the inflation forecast look like for those three groups, and how the inflation forecast error look like for those three groups. How much error? Basically, generally speaking, we see that the inflation error happens more likely for the low groups, especially for L2 groups. Next slide, please. To actually measure about whether there's some kind of information diffusion, we also follow the Granato-Krauss idea. So we do what we call the Granger causality test. We want to see like which causes which. But actually the high group inflation expectation causes the low group inflation expectations, or the opposite, the other way around. So basically, according to the Granger causality, we only see, interestingly, that high group inflation expectation affects low group inflation expectation. However, the low group inflation expectation has nothing to do with high group inflation expectation. So that means we can only see a one direction, exactly how we put it in the theoretical model. We only think that how high group information affects the low group expectation, but low group expectation does not go back to the other side. And that's how we form our theoretical model based on our empirical observation. Next slide, please. Since we actually believe that interaction happens, And we believe that we believe that the interaction may create error. So what we are trying to do is we want to measure two variables. So simple, two variables. One first variable is about the interaction error, which is the sigma square E. That's what we show in the empirical model. We want to calculate, we want to measure sigma square error. And then we also want to measure the forecast error for the high group, which is like just about the forecast, the inflation expectation error from high group, the MSEH. And after that, we want to see whether these two variables are how the relationship between these two variables. That is what we want to test. That's what we call testing the boomerang effect. Then we can move on to the next slide. To test it, certainly we need to actually calculate two things. And we strictly, because I think we try to do EITM, so we try to strictly coming from the theoretical model to create our variables. So in this case, based on, I'm not going to go too deeply regarding about how the theory and tied to the empirical part here, but at least I want to make sure I mentioned that here that the ET, which is the measurement error, the ELT -1 there, is strictly coming from the model that we calculate, and then we collect the data and calculate that sigma E squared, theoretically coming from the survey data. And we create that variable in this case, and then we can move on to the next slide about measuring about the MSE, the mean square error. Mean square error is nothing more than the actual inflation minus the inflation expectation from the high group, and then we take the square, we add them up, divided by the number of periods, and then we can actually measure the MSE for high group, which is the traditional way to measure the forecast accuracy for anything. And so we follow the same way. So now we got two variables, the interaction error, which is sigma squared E, and also MSE, the forecast error for the high group. So according to our theory, we expect that the interaction error will have effect on the forecast error for the high group. That means whenever we have interaction going on, the high group would got affected in this case. So what we are trying to do is we do two tests. We do the unit root test to make sure that they are related. And once we think that they are related, we want to use the Johansson's integration test to test how the relationship look like. And that completes the empirical test. Next slide, please. All right, so here is a unit root test. Because the thing is, what we did here is that we basically generate two time series variables, right? We have the sigma E square, which is the interaction error, and also the MSE over time, which is like the forecast error for the high group. So what we want to make sure here is that whether the properties of these two variables actually make sense, so that we can move on to the co-integration test. What we found that is that like these two variables are I1 process, the integrated order 1. So that means they are non-stationary. Because they are non-stationary, and we want to see whether they actually co-integrated. So that will be like from here, from this table here, what you can see that from the panel A, which is you can see MSEH, sigma squared EL1, sigma squared EL2, and you can see the conclusion on the far right side. You can see I1, I1, and I1. That means these three variables are non-stationary. Because they are non-stationary, but I think once we take a difference, these three variables are stationary. So that means they are potentially integrated. They are potentially integrated. If they are potentially integrated, the question is, are they really integrated? That will be our next step. We want to do the co-integration test. Next slide, please. So finally, we do the Johansson co-integration test to test whether these three variables, are they related to each other or not related to each other? So it turns out we can find that they do have relationship with each other, and you can actually see from the conclusion row. For the conclusion here, we actually see that they have one co-integrating relationship, which is coming from MSE and also the low group, which is the L1 group. And then you can see the second column, which is MSE, and the second the L2 group, and they both actually show there's some kind of correlation, a co-integration relationship. And we also see that even though putting three groups together, the high group and L1 and L2, we see two co-integration relationship. That means L1 and L2 are both related to the MSE for the high group. So basically, we found exactly what we found in the theory. And more importantly, do we actually see what we found, that more interaction error, we actually generate higher forecast error for the high group? Do we see that? Basically, we found that from the last row here, the estimated co-integration factor. This is a factor, so that's the reason why everything is on the one side. So whenever you see a minus 29, that means it's a positive relationship between two variables. Okay, so let me say one more time. Whenever you see negative value here, negative means positive relationship between two variables. Okay, so because this is a factor. So in this case, we can actually see that whenever we see interaction between two groups, then the MSE would be larger. And the thing is, whenever we have a larger interaction relationship, then the MSE will be larger. In this case, not only for column 1, for column 2, and for column 3. So, however, if we look at column 4, if we don't take into MSE, the high group into account, nothing happened. So basically, in this case, what we actually observe is that the relationship only happened between the low group and the high group, but nothing to do with between low groups within low groups only. So that confirms that the relationship only happened between high and low, but not within the low group themselves. The last slide, we're actually showing you about is it really about like the interaction affects the forecast error? Would there be any possibility to actually go the other side, like forecast error affects the interaction? What we actually found, we used the Granger causality one more time to see a direction. So that's exactly what we observed in the data or in the theory. Though we only believe that according to Granger causality, we found that only the interaction error affects the forecast error, but not the other way around. That fulfills what we observed in the theory, what we found in the theory, and that concludes the result here. So our data here, actually, we use our theoretical model and then to build up the relationship, and we try to use the data to see whether the theoretical argument can be supported by the theory, and that is what we did here in this paper. That's all I have. The last slide will be just like showing you about like putting these together. And then there will be the unit root, Johansson test, the Granger causality to test the theoretical model. And that basically how we put step 1 and step 2 together to have the step 3. My slides will be. Thank you.
All right, good. And let me see. I can bring Jim back to the spotlight. Then we can have some question and answer time. And have some. Sorry, I don't know how long did Marianne raise her hand here. Apologize, I missed your hand. Marianne, can you speak up? Do you have a question? Dr. Stewart? I see your hand up. Can you go ahead to speak up? Oh yeah, I think this is something that, let me see if this is something to do with the Teams set all the attendees mic muted. Apologize, and used to be all camera and mics up, but now by default they mute everyone. Marianne, please go ahead. Can you
Carl,
hear me?
where have you been? I sent you a chat message about half an hour ago saying that everybody's mics except for the participants were muted. Were you like asleep at the switch?
Apologize. I was
just
number one. I was working hard to scroll the slides for Jim and Sunny, and I was a diligent worker to scroll the slides.
Okay.
Number two, I'm really mesmerized with all these slides, and it's still so illuminating. I'm still processing the intensive amount, the intensive information. So I can tell why you back then at NSF will endorse this project back then when you were a director at NSF. Marianne, please go ahead.
I raised my hand for a question just a couple of minutes ago. Jim and Sunny, thank you. My question is this, and I'll try not to make it too detailed. In your EITM of rational expectations, which is a concept and idea that's been much explored in economics, as we know, but we also know, courtesy of people like Richard Thaler and Gerge Grenzer and Amos and Tversky, Tversky and Tiedemann and others, that the world is not one, the real world is not one of rational expectations. The real world is one in which education does not proxy for cognitive information processing ability. We also know that the information that is out there in the environment is often very murky. So ability to have access to that kind of information is highly problematic. And so I'm asking whether EITM can help us understand a real world in which there may be low cognitives and high cognitives, but for the most part, it's populated by a lot of low cognitives for the reasons I just mentioned. They don't have the time, they don't have the effort, they don't have the cognitive functioning capacity, the information is a mess. And when people do access information about something that might interest them directly, such as inflation in the present era, they come to that information with lots of biases and prejudices. Can EITM help us understand that kind of messy world of information processing?
You want me to answer this, Sonny?
Sure, please.
Yeah, so I would say it can, but its limitations are the mathematical characterizations of what you just described.
Mm-hmm.
So I could see going with an experimental model, right? I think that's one way to start to test this. In terms of modeling the messiness, I think you'd have to move. So this is a very particular set of assumptions. And so at one level, and again, that's one of the things about this, the assumptions are all out there for you to see. This is what we got. It's consistent. But I would say to build on this, you'd want to relax the expectations constraint that we have right now. Maybe move into some type of behavioral model, something that Thaler has. I've not looked at that recently. That'd be one. Another is moving to adaptive learning, which involves, in the end, you do get it right, but there's a lot of ups and downs on the way to it. That's another way to characterize it. But what you're suggesting, Mary, is exactly right. Those are the things we want to get to. And I think formalization of those things is the next step. I mean, I think as this goes forward, we're going to have better and better ways of looking at these things. I mean, think about something like agent-based modeling. Forever, we had what we called representative agent models. And in our book, I think we have 2 chapters relate to that. With agent-based modeling, it's another tool, but you can have heterogeneous agents. I mean, when we can actually start simulating all the things you just mentioned, you could have a bunch of people who don't know anything. And you could fit them with these specific biases in there, and you could simulate all that and match up with the data. That'd be another way to go. But the answer to your question is, what you're saying is exactly where we need to be. We need to keep looking at what aren't we getting on what we have right now. In the meantime, build accumulation of what we do have that's coherent, even though we know it's not good enough yet. And even when we get to that part, there'll be something, even when we get to where you're talking about, there'll be something we come up with later about emotion, all kinds of other richness, the richness of people's behavior that we're not capturing right now. So the answer to what you're saying, I think you're right. And the question is, how do we improve our analogues?
Okay, thank you, Jim.
Hey, by the way, Mary, I don't know if were you here for the first part of the talk?
Yes, it was very gracious. Thank you.
Well, yeah, I'm glad you were there. Yeah, because it's, thank you for everything. I mean, God bless you.
We'll talk later, Jim.
Okay.
Yeah, Mary has been here since the first hour, and I think I did not notify you because I think sometimes I spotlight the guest. Yeah, I do not want to do it too
Sometimes I like
to
to
get
brag
the
about
guest
people I know.
embarrassed.
Yeah, sometimes I want to brag I know that aren't there, so they don't know.
Thank you for
Carl,
supporting
are
us,
there other questions?
Mary. Yeah.
Other questions from
please.
people?
Yeah.
No, I don't have
Peter,
other
do you have any
questions. I'm
questions
asking
from
if
the
there are
Taiwan
other
students?
questions.
Yeah. Peter? While you're waiting, I think I have some general questions. So actually, I've been learning about EITM kind of a while back, and Marian was a director, and Harold was the director at NSF, and they introduced the concept. I think I think I learned from you in a couple of methods conferences, and directly from Jim. Now I have I'm in the direction of moving to some data science training to our students. So in a particular way, we call this machine learning and building machine learning models. So the machine learning models are they acknowledge that from Leo Brame and 2001, they acknowledge that they focus on the data. They put really little emphasis on the formal part or the theory part because they are concerned about prediction. They use different kinds of algorithm to process data to come up with the best prediction of the final outcome. Then they use different features and plug in multiple combinations, regularize or shrinkage of these variables, even they're highly collinear. Okay, then in a nutshell, and the machine learning trend now is more focused on prediction, but not the theoretical part. Now there is a revisionist kind of movement thinking about how these models could be interpreted. To make these models interpreted, they have to come back to the parameterization of the models or the choice of these variables. So lots of computer scientists and even they use neural network models, they acknowledge that the models are not explainable. So that is that making EITM particularly important in the current big data world, and they only know about how to predict. Okay, that is right, but they don't know what is behind that. And now I have to admit I'm more like a frequentist. I'm a student of Harold Clark, and so I learned all kinds of time series models, co-integrations, and so I confess I'm more empiricist. And on the formal part, but we look back, and it is extremely important to look at how you can figure out the theory underpinning of it is then just do wild guesses. I think you earlier talked about wild guesses. Oh, could be a theory like this. Could be a theory like this. Or could be some kind of model misspecification. Could be some kind of measurement error. And in machine learning language, there is one part what is called a reducible error versus irreducible error. So that pertains to the part about something we still have to take no matter what. There's kind of error we cannot know. But the reducible error, that is the part machine learning people, they just try different combination and figure out how do they limit this or minimize this, but they could not explain. So that is the very important part that EITM can come into play to bring the theory building part and the interpretable part of all these machine learning models. This is like a black box, and I think a lot of the machine learning people could not answer. They're leaving it to the future people, and are living in a black box, not to open it. And so, how do you address that gap?
You want to go first, Sonny?
Yeah, go ahead, please, Jim.
You want to go? You sure?
No, go ahead. Yeah. I can go second.
So they're facing a problem. They have nothing ex ante, if I interpret what your comments were, right? Mm-hmm. They don't have, there's no basis for, I mean, I don't do machine learning, but I was trained as an empiricist too. Mm-hmm. And so let me give you an example of how theory can really affect prediction. It was driven by a pattern in the data. And it was something called the Phillips curve. I don't know if everybody's familiar with that. It was a relationship between inflation and unemployment. Yes. Mm-hmm. Mm-hmm. Okay. Mm-hmm. So there was in the 50s and early 60s, there was an assumption based on the data. There was a structural relationship between inflation and unemployment. You get high inflation, you get low unemployment, you get low unemployment, you get high inflation, right? There was this, and there was a trade-off. It was structural. It's thought to be in stone, which in the social sciences we should never believe, but that's another story. In any event, so it turns out, okay, so there's the empiric, that's the puzzle, that's the pattern, that's the structure that the empiricists thought existed, and that was the truth. Mm-hmm. Well, it turned out, if you look at it ex ante and you assume expectations, behavior, now it became a question of behavior, and what people were finding was the behavior is inconsistent with that macro result. And so it depended on how expectations were formed. And so there you have ex ante discussion about if people behave this way in terms of expectations, the Phillips curve is not existent. Mm-hmm. The structure disappears. So there's a case where theory informs the pattern or the pattern not being there. And so what I would argue is, I don't know what the problems are they're looking at in terms of the machine. You could actually, if you want to send some of these things to me or in the Sunny, that'd be great. And we could, there could be some things we just think about in terms of the theory behind what they're saying. What are the concepts they're looking at behaviorally? Because we're behavioral scientists, right? So we need to be looking at behavior. That would be where I'd start. And then you start modeling these things, listen to the stories people have and what they're saying. We're trying to formalize some of these things and see what the patterns you get ex ante before you even get to the machine learning part. And then you can bring that in later if you want to say, oh, okay, this is consistent with that. It's not the truth, but it gives you an ex ante explanation why you see what you see.
Mm-hmm. Mm-hmm. Yeah, if I can also jump in, I really like what Jim's point out about the Phillips curve idea, because I think that is the great way to think about, like during that time, like when A.W. Phillips actually published his paper, I think it's 1930 something, like 1958. So he just found that the relationship. Okay, that relationship, when inflation goes up, unemployment goes down. When inflation goes down, unemployment goes up. And found he has no, basically it just showed this the result. And that's it. Like the data tells us why that was the case. And then we want to come up with the arguments, right? And then after 1958, and then people start coming up with ideas of why this is the case. How come we see a relationship between these two? And then we come up with the supply idea, we come up with demand idea, then we actually see the situation. And then people actually, because the talk about like Phillips curve is specific about economics, then people find that, oh, you know what, if this is the case, if I want to actually make the economy to be low unemployment, the best way to do it is just create inflation. Inflation goes up, unemployment goes down. So the good way to just make inflation happen, print more money out. We know that inflation can actually happen by printing more money. So why don't you print more money out? And then like that's what happened in 16th and 70s. Like we print money out and we see unemployment went down. But the thing is not for a long while. But the thing is like people actually start realizing that it's not only the data will give us the complete story. We need to have an argument. The thing is once you get to 70s and 80s, turn out this kind of relationship broke down. It doesn't happen any longer. And then like why? The data now doesn't support what we observe. and we need to have an argument. We need a reasonings behind it, right? And that's exactly what Jim actually mentioned, and I think that's a great example. And going back to your argument about or your idea about machine learning, I completely agree. Like, talk about machine learning is nothing more about prediction. They do not care. It's almost like Jim, what's the paper that I just ran 2 million regressions?
2 million regressions, yeah.
What was the paper? Who was that? Edward Lehman, right? Edward Lehman, actually, he published a paper in AER in 1980 something. And he wrote a paper actually called "I Just Ran 2 million regressions." Basically, what he found, what we try to do is just exactly almost like a machine learning idea. They ran regression 2 million times to figure out like what variables can actually explain economic growth. They don't care about theory. They just want to see, okay, what variables can make it happen, like extreme bound. So this is almost like the very original idea of like machine learning. I don't care about what variables they are. I just keep running until the point that I figured out these factors can help me to predict what happened next, right? And that's the situation. However, it doesn't tell us what the behavioral situation look like, why that happens, right? Nobody knows. Just like, I think it's all about like what we actually observe in the history about academia. In the past, data is so hard to collect. It's so difficult to get data. So what can we do? I think argument, theoretical concept, and those becomes the mainstream until like after like the technology comes in, right? Data becomes so cheap. Computer becomes so cheap, running regression so cheap. I can hit a button in less than 1 second, I get the result. In this case, the cost of running regressions is so low that, and the data is just so much that we can keep running regression without paying too much cost. Not like 50 years ago, 100 years ago, or you have to have a big, the mainframe to run regressions, right? So in this case, the running regression is so costly, theory is relatively cheaper. So, and that's why we put more effort on theory than data. And nowadays we go the other way. Because thing is, data is cheaper than theory. Because thing it's so costly. It takes so much energy to create a new concept with the new theoretical models. And that makes the whole trend go the other way. But that's the reason I think we need to have a balance. We need to have both theory and data to give us a better idea how the world works. And that's how I put it.
Yeah. Good. I want to check, Peter, do you have any questions on the side first? And I have some questions follow up too.
Sure. Yeah. Thank you, Sonny. I think that I totally agree with the idea that you just brought about. It's about time, right? Because we are moving from the theoretical as a mainstream, and then now, like you said, it's the cost. Now the machine learning is now cheaper in the sense. So I think this is what makes EITM more important at this point of time. I think this is a very good insight here. I do have some relative kind of questions from my students here, because more of the audience here are master students, at least in my part. So they with less sufficient training in econometrics, formal or theoretical modeling, which means that they might be more comfortable with collecting data and applying to the theoretical models that had been proposed or tested. So what do you suggest the students move toward the path of adopting EITM framework, or where to start with? It's a more practical questions for them.
So let me say, between Sonny and I, he's much better at mathematics than I am. It's always been a grind for me. But I can tell you what I did, and I learned this from Lynn Ostrom as well. You work with people who can do things you can't do. So, there's this famous story about a comedian in the US, his name was Jackie Gleason. He couldn't read music, but he wrote music. Now, how did he do that? He had a picture in his head. And what you want to do is work with people that are, my sense is people for the most part, in political science, or like I was, and still am for the most part. I mean, I'm much more comfortable with empirics, not even close. I can do some formalizations, but I usually need help at some point. And so what I would advise anybody to do as you're trying to build this bridge for yourself is to work with somebody that can do some things you can't formally. I'm assuming empirically you're going to be just fine. It's the formalizations that get you stuck and frustrated. And I would say that's probably the biggest barrier to people adopting EITM in a larger amount. I think that's why it's going to take a while. I mean, we're getting there, but it's still not, it still hasn't taken the hold I thought it might, but I'm patient. But the issue is the math part's difficult and it pushes people away. And so find someone in a discipline that has a little more mathematics than you do, or is more formalization training, they're stronger at it, and partner with them, co-author with them. And all of a sudden, you're picking up things you never picked up before on your own. You wouldn't have, except over a longer period of time. So right. And that's what I learned from Lynn Ostrom. She said the same. She said she worked with psychologists, economists, and she was, she was incredible, but she needed help with some of the formalizations. And but she had the picture in her head. That was the point. And she learned the formalizations. Maybe she couldn't do every step. She had the basic framework in her head. So she'd go to someone and say, I've got the following thing. Can you help me fill in the details? So that's the way to do it. It's collaboration. Okay. Work with people that know something you don't.
Mm-hmm.
First of all, I don't think
yeah.
Mm-hmm. Go ahead. I just want to say that Jim is completely not true. I think Jim can do a lot of sophisticated analysis here, but but the thing is, we just work together. To me, I think not only the math part is, I think Jim mentioned about the math part is important. That's true. But the thing is, I think the idea is important. Actually, having the concept important. For example, when I present the inflation expectation idea, right? Without the first idea about seeing what happened in the real world, is you can have a lot of good mathematicians in the world. They would not, if they know about some new ideas or some good ideas, and the tool is just tools. You have all the screwdrivers, the drill. Who cares if actually you're not thinking about creating a table, you're not creating a desk, you don't know how to actually the desk structure. Not the tools, are just the tools. So I think I completely agree with Jim, and also I think the idea that coming from Jim, or I think that the complementary part is actually important and making something happen.
Okay, yeah, that reminds me that what Carl and I we're doing some project or initiative. We try to bring the data science and to all the students from the social science side. So we try to invite. For example, I'm running between two classrooms today.
Right.
Because the other behind this wall, and then on the classroom, and I invite another instructor from computer science, and then they try to introduce how to analyze the data, big data, and then introduce the basic idea. Of course, we know that it's impossible for our students to become a data scientist just in no time. It's impossible. So our idea is that how to create some learn some common language so they can collaborate with some.
Very good.
From the other side. Yeah, that's what we're doing. And then exactly the same as what you just mentioned, right? Find someone who knows more about mathematics, and then we have the idea, and then let's do something together. So that's about collaboration. I think this is the trend. And then, yeah, I'm glad to hear that, right, Carl?
Yes, you'll have you'll be doing, I mean, when I started doing this in the late 90s, I mean, what I'm doing now, I never thought I could get to, but I worked with a bunch of people, Sonny in particular, and I have a foundation now, and the same thing will happen to every student that's listening to this. If you collaborate, find people to partner with, you'll get there faster, and you won't forget it either.
Mm-hmm. 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 Then a footnote to add that Jim just cited Ostrom being the first political scientist getting a Nobel Prize.
Second.
So hopefully we can get it. Second or first? I think it's
Herbert Simon was the first. Herbert Simon.
Scientist.
He got it in 1978, which I remember economists were furious when he got it. They were less furious when she got it. He was the first to start bringing in things like psychology into economics.
Okay.
So he predates Kahneman and Tversky. Satisficing, this idea of satisficing, he was the one who went after the utility function and said, wait, what about this maximization problem? I don't know if that's right. He had very good mathematical skills. He was also very much into public administration. But Herbert Simon was the first.
Okay. Then I want to come back with my question. If it's okay, I still can ask maybe one or two more questions. If it's okay with Peter and then Jim and Sunny. So another area that we are begging for more emphasis, more training is what we call causal inference. I think Sunny demonstrated the models or the tools which will be great for causal inference using graduate causality test and co-integration and Johansson test. This is something really badly needed for data science too. And how do you use these tools to better test that causal to provide a causal inference? Because now again, the EITM, the TM part may be more data science is doing more actually on the M part, not even the T part. Then empirical part, which should not be a problem. They're both about pictorial data, big data, and but now it's really time for the data scientists to think about the T part and also the I part, and that is much needed. And then I want to also add one more example. And Hera and I did some modeling. We did run 2 million models. we use a method by a Stanford sociologist by the name of Christopher Yang. And similarly, we do all the combinations to try to literally run millions of models with all these variables on the right hand side, try all these combinations, try all this parameterization. Now, one thing that could be a good application is called the valence model. So valence model is not starting off with the formal part, but starting off more like experience. Then Harold did really ran around a lot of models. Then he come back to find out the most important variables, the 3 variables that explain valence folding or voting. And so that is the part that could be further developed. Thinking about that, this is like information processing. So how much the information is prioritized, and what is the most important information first, then we'll give like a cue or give heuristics to the second most important variable, the third, which is related to partisanship, leadership, and leader image, and also the evaluation of the economy or economic voting part. So these are in the train though, but something we still have to further build. I hope Marianne is here, and then we can even think about how we can even building stronger and of all this information expectation, and then how they could be prioritized, could be more formally built in the theoretical model. This would be something I'm thinking out loud to see whether this could be something we can develop in political choice models rather than economic models. Yeah.
So you're saying data's ahead of theory, right?
Yes. Mm-hmm.
Okay, so
but imagine,
so the next thing you think about is, what are people doing? What are they doing to get these certain results? Is it a decision they're making? Are they interacting with people? Are they bargaining with somebody? I mean, what are the models that are out there? And then you could start tweaking them and seeing if you get these, if you get a prioritization. I think that's what you're saying. to one thing over another. I'd have to look at the data, you're the model you've got, the empirical model, but I always start with the question, what are the people doing? What's their behavior? And then you can start building things. Now, it may not be right, but you're building an ex-ante foundation now to see if you get those results in your tests. And then someone can come and tweak what you've got, but you're still within that framework. So the parameters follow each other. You're not getting this, the whole system change. That's the thing that's so troubling about people that do stepwise. I mean, I remember John Aldrich told me, so if I catch anybody doing stepwise regression, it's an automatic F in the course. I mean, anybody can throw in more variables. The problem is the whole system gets ratcheted up and you don't know what's going where at that point because of all the correlations. But anyway, my point to you is start with the question, what are people doing? And what do other people say they're doing? And see who's done something on this already, and look at if it's not a formal model, what's the verbal discussion? Look for those behavioral concepts. I constantly see people saying, well, they expect this, or they learn that, or they're bargaining with so-and-so. And they use those words and then they don't model it. And I'm saying, damn it, we've got the tools, start doing that to build that bridge.
I would say that's exactly right. Carl, there are a lot of tools available already, and we don't need to create a new will. Right? The thing is, we actually have all the tools. All we do, we want to actually find ways to actually see what would be the closest model that would be related to something that we want to do, and is there any way we can twist existing models? And hopefully, by twisting the model, we'll create some new ideas from the new model. It's not a completely new model, but the thing is, will be new enough to explain something differently. And I think that will be the more effective and more efficient way to think about the theoretical model. Otherwise, it will be very difficult. It's very costly to do theoretical model if we always, every time we want to create a new model, if a completely new one, and we put all the energy on think about new things. Unless we are talking about Robert Lucas, right? Okay, he was the one, and not even him. He was not the actually one actually making rational expectations, right? The thing is, he was only came from one very important idea, one paper by
John Muth.
John Muth, exactly. Muth, that paper actually only one or two people can understood that paper during that time, and then finally Robert Lucas actually, oh, that's a good idea. Why don't I twist that and make it to be called rational expectation? And then later, other people think about, oh, rational expectation is just too strong. Why don't we actually twist the idea, make it to be learning, adaptive one? So that means people are updating the expectations over time by getting more information. And then we keep talking about different ideas, coming from the original one, then people keep twisting and twisting and twisting the idea and getting the new ideas. So it will be difficult to get a brand new, but twisting ideas is always, the marginal cost will be always lower than have the brand new cost, right? Yeah.
That's right.
I think that gets to Mary Ann's point earlier about, we were using rational expectations. The thing about rational expectations is so important is that mathematically it's very easy to implement. So that was another reason why we used it. It was also, you're putting a flag out here saying, if people behave this way, this is what can happen. And of course, we've now moved back from that. We've relaxed that assumption. Adaptive learning is one way people deal with it. Bayesian updating is another way people deal with it. I mean, there's more than one way to model expectations, but you had the extremes back then were rational expectations and adaptive expectations. And in the case of adaptive expectations, you never caught up. You're always in error. With rational expectations, you're always, except for random error, you're always on point. So the errors are just random. You're not systematically wrong. And that's the key thing. But the information requirements are quite high. And as Mary Ann said, we know in most cases that's not true. However, there may be some cases where people know what's going on and it's an appropriate tool. But again, what your data is telling you, what your idea is, dictates the type of modeling concepts and analogs you're going to use.
Mhm. All right, great. Really illuminating. Peter, do you have more follow-up questions or remarks? Can you unmute yourself? Yeah. Still cannot hear you.
I didn't turn on the mic. Sorry.
Oh,
Yeah.
yeah.
Yeah. I just for a moment I forget I need to use this one. I thought just like you do. Yeah. Not so far. I mean the question's not here. I didn't see anyone raise their hands, and so I think maybe Carl, you have to take this final 5 minutes opportunity if you have any more question to ask. Any?
Yeah, my expectation is that could be another hour. Yeah, really further develop a Harris and valence, politics and valence voting model about particularly borrowing from Sunny's slides about the boomerang effect and also the information, how this is highly informed or lowly informed, and because we generally believe that voters are cognitive misers. They don't want to think, don't want to spend time and effort to get more information, no matter how educated or how they are, how they want to be informed. They want to be easy information and a cheap information they can get. This is why the idea about the valence model is they get easy heuristic and follow the party, follow the leader, and follow the some easy to get index. But think about this, and this is something that I really like to have another hour to use Sunny's model about this. It could be a lot of errors, and these errors will make the highly informed actually that increase, or then could be more effects to the followers. Some and then, for example, I will ask Jim who you want to vote for. Then Jim is the most informed one. Then I would if Jim is getting some errors, then my error would be even more because I'm following him. And so that is something I think this to be a lot of potentials in doing this kind of models, modern technique in using EITM on the valence politics. Yeah, I think this will be. I do not want. I should not take more time. Yeah. Yes.
Yeah. Well, there's this question about the high group and low group. I'm sorry, maybe we are running out of time, but I think the very short question and a short answer, please. And just like the information diffused from the high group to the low group, right? And then maybe we are running too fast. So how do you prove that it doesn't work the other way around? Yeah, you mentioned some point about this, right, Sunny?
Yeah,
yes.
well,
So
let me interrupt and then Sonny can take it, but it goes back to a literature 60 years ago on issue publics. You guys familiar with that? These were the people that were the opinion leaders that people with less information would rely on. It could be a neighbor, could be somebody. This goes back to the Columbia studies, if I remember right. Anyway, that's where this is an old political science concept, and then we took that. We looked at the more modern literature, and we still found it's also in the finance literature. You have this idea that some people are considered experts or focal points that people will depend on them to get information. They will help inform them in their decision. And Sonny can take it from here. I'll be quiet.
right. So yeah, that's right. So in the literature, it has been showing like this. And I think from when I first talked about Jim's paper, the 2000 paper, he basically showed that only the high group, the more informed group, can affect, like have a greater cost, the low inflation expectation, but not the other way around. So the greater cost only go one direction, but not going to the other direction. And this also confirmed from our paper that the paper that I present, and also like I use exactly the same Granger causality. We only see one direction, which is the high informed group affects the low informed group, but not going to the other side. So in that case, that actually confirmed what Jim mentioned about the literature, his paper, and also like when we do the follow-up test we actually get exactly the same result. So that actually provides us the good justification that our model only go one direction, but not the opposite direction.
Let me add something. So this was back in my empirical days. We used vector autoregression. And so we just let the data. So we assumed, we argued, not formally, we just made an argument that it's the high group will inform the low group, and there won't be any feedback. There won't be any reciprocation. So that was the straight empirical paper. And that's what we found.
Okay.
But here's the question with the formalization, look at the richness we got. We were able to not only look for that kind of direction, but we also got the boomerang effect, which we never have uncovered if we had just left it as an empirical model. So that's what can happen. Remember, ex ante, you can start toying with the model and say, wait a second, if I do this, I get this other prediction. And that's what the boomerang effect is what makes that paper important, the chapter important. Is I would never have thought of that.
Yeah,
and I think there's some other literature actually shows that too, that well-informed people can actually get their inferences confounded by looking at things that the less informed are doing.
Okay.
Yeah, we found it very interesting when we actually first developed the model. And we found that, because the thing is, without doing the model, without doing the mathematics, we could not even expect that that could happen until we actually we create a model, we even simulate the model. When we do the simulation, we generate the new data, and then the data confirm this is the case. And we finally we know this is, and then we try to understand why that's the case. And then Jim and I keep talking about what's the reason, and then that's because it's all because of the interaction, and the error comes in, and the error make the high group did not know what was going on, and they thought that they got all the information, but because of low group, because they got as exactly what Carl mentioned, right? The thing is they have a more error going on, and that makes them not knowing about why that was the case, and they make a higher forecast error as well, be due to the interaction.
Yeah, the low group had a higher error than the transmission of the information from the high group to the low group. The error was of such, if it could be of such magnitude, that would confound what the low group was doing, but that would affect what the high group was expecting. That was the issue. That's what we found.
All right. Thank you. Yeah. All right, Carl, I think we're running out of time, right? You wish that we have another hour, I know. Yeah.
I wish.
We have to wrap it up now.
It's like a feast and great. Okay, now I think I would just wrap up. Thank you so much, Sunny and Jim particularly, and I know that it's late at night, and I know your busy schedule still accommodate us to give us a great talk at the Colloqium. And I want to double check with you. It's okay, we can disseminate your slides and to students, and also we will post this video to our YouTube channel under Data Analytics Colloqium if I get a consent. So great. Now I think and thank you very much and for coming to us to give this very important talk. And also I will also send the link of the book with the same title to the audience. And to remind our audience, our next week event will be of a different time because we have a scholar from East Coast, and this will be Skylar Kramer talking about the network science. And the time in Central Time will be 7 p.m. and in Texas. In Taiwan, because of daylight saving time change, it will be 9 a.m. in Taichung. Yeah. All right. Well, I want to thank you again and give a great round of applause to Dr. Jim Granato and Dean Granato, and also Associate Dean Wong. Thank you very much. Thank you.
Thank you, guys.
Thank you so
Thank
much.
you very much.
Thank you, everyone.
Thank you.
Bye-bye.
Yes, thank you.
Yeah,
Bye, everyone.
Good night. Good night.
Bye-bye.
Good night.
Good night. Bye-bye.
Okay, Carl, thank you. Yeah, just for a couple of minute things. Maybe there's another idea about this high group and the low group, given those like inflation or those kind of information, maybe the high low, I mean the information flow from high to low.
Mhm.
And
Mhm.
can you think of anything else? Because in old times, we have a limited channel or platform of the information dissemination. But nowadays, information is not just like they use paper or radio, television. It's different now. We have all kinds of information online, right? So all kinds of data online. So does it make any difference of this, information dissemination?
You're
What?
exactly right. Actually,
Yeah.
there could be something we can now we can if we do not do the formal theory part, we will just do the guess. We can try experiments. We may do maybe 100 studies, but we can come up with a theory from all these studies by chance to come up with a strong theory to suggest how information flows and highly informed agents affect the lowly informed agents. But it could be something we can even see if it could be different in the new digital media world. Because, for example, highly informed could be coming with a motivation. Imagine that. So this could be coming from orchestrated effort, what I call cognitive warfare effort, and will that be strongly mediated by this coordinated warfare effort? And then, oh, this is all this party or this government or is doing this kind of bad things, bad policy to the general well-being of the people. So this we have more information, but this information could be bad information. So highly informed here could be a different implications in this case, because you may have read 100 stories from the media, but how much this will be the story about the Fed supported, evidence supported story versus the KOL supported, influential people supported story. So information, and in this case, could be high volume, but could be bad quality. So that could be something we can study. So how can we study that? You can try different experiments, but one thing that Granato and Wong is putting forward is, what is the theory behind it? How do you formally build this theory before we do the data? Yeah.
Yeah, it's just an idea.
Great suggestion.
Just
a great idea.
You have to think of nowadays the information is so much out there, and then there could be some bandwagon effects, something like that. You don't need to be informed about KOL, right? So everybody does that. I just do the same. So this could be another story. So I'm just an idea.
Yes.
So
it's a great idea to do that.
We can talk about that later, though. Yeah. All right. Thank you.
Okay.
Yeah. And good.
Thank you.
Thank you for all the audience, and thank you for coming aboard today. And stay tuned, and then come back next week. In Taiwan,
Okay, see you all next week.
Yeah, 9 a.m. next month.
9 a.m.
All right. Thank you,
next
Carl.
week.
Bye.
Bye.